Hello everyone, I'm going to be talking to you about rational functions. What are these functions? They're expressions of the form f of x is equal to p of x over q of x, where this p and q are polynomials, which we talked about last week, where the polynomial on the denominator, this q of x, cannot be equal to 0. And again, these are rational functions. Now, why can't our q be equal to 0? So recall from last week, we were saying that if we had some value, it could be a constant or it could be a function, but whatever it is, if we have this being divided by 0, that value approaches infinity. Now remember, infinity is a concept, it is not a number. And this little arrow sign here, this means approaches. And in math, we say when a function approaches infinity, at that coordinate, it does not exist. All right, now let's look at an example to get a better idea of how to think about this. Let's look at the function 1 over x. You've probably seen this before in high school. And if you forgot what it looks like, that's okay. Let's consider a few different values. Let's consider some negative values, maybe negative 100, negative 100. Maybe we can do negative 2, negative 1, 0. And then we also want to see what it looks like when our x is positive. All right, so when our x is equal to negative 100, our f of x, if we plug it in, we're going to get negative 1 over 100, which is a small number. As x starts getting closer to 0, the value of f of x gets a little bit larger. When we get to negative 2, we have negative a half, and then we're going to have negative 1 over 1. When we have 1 over 0, this value does not exist. Okay, because this is a really big number, it's infinity. So that means that when x is equal to 0, we're never going to be able to cross that green line that I just drew in there. So our function f of x is equal to 1 over x never touches this line. Never touches this line. And what does that mean? It means that x equals 0 cannot be an input of f. More precisely, we're going to have to exclude it from our domain, but we'll talk about that more later on. All right, let's go back to our table of values. If we have x is equal to 1, we don't have a problem. Our f of x is 1 over 1, and then we would have a half, and then 1 over 10, and then 1 over 100. So if our x's are positive, our y's are positive. If our x's are negative, our y's are negative. And as x gets really, really large, the value of our function is going to get closer and closer to 0. Same thing on the other side. If x is getting more and more negative, the value of our function gets closer and closer to 0. But for a function, as we approach this line here, if we're positive, x is going to get really large. If x is negative and gets close to 0, it's going to get really large, except in the negative y direction. So our function looks something like this. All right, this is our f of x. So what did we say there? So we said, notice that as x goes to infinity or negative infinity, our 1 over x goes to 0. However, as x goes to 0, our function is going to go to infinity. Now this line here, this green line that I drew, is a line that our function is never going to be able to cross. Lines like that have a special name. They're called asymptotes, and there's different kinds of them. In this class, we're mostly going to be looking at two types: vertical and horizontal. Let's first talk about vertical asymptotes. What are these things? Well, if we look at a rational function, and we do look at the points or the coordinates where q of x is equal to 0. So the x values that make q of x is equal to 0, those are the coordinates that our function is never going to be able to cross. Okay, so say we have a function where I have x minus 1 on the denominator. We don't want this to be equal to 0, which means in our case, our x is not going to be able to equal 1. So we can almost think about it like we have a line and x is equal to 1 that our function will never be able to pass. It'll never be able to go across there. Okay, and our function, our function could look different. There's different types of functions. Maybe it looks something like this. Okay, but that line right here, what does that represent? This purple line? This is the x that gives q of x is equal to 0. Now, horizontal asymptotes. Similarly, these are going to be lines that our function also cannot cross. But to find these asymptotes, we like to look at x as it gets really, really large in the positive and negative direction to see the general behavior of our function. So I have an example here. If f of x is equal to 1 divided by 1 plus x squared, regardless if our x is very large in the positive or negative direction, because it's squared, the denominator is still always going to be positive. So this function looks something like this. Okay, if our x is equal to 0, our y is equal to 1. And we can see that as x is very large in the positive or negative direction, our f of x, it approaches 0. Again, it never crosses 0. And this thing here is called a horizontal asymptote. And it tells us the behavior that long term, as x gets really big, goes to 0. Slant asymptotes, they sometimes look like the example that I drew out here, and we find them by performing long division on the numerator and denominator of a rational function. We're not going to be doing long division like this, dividing out polynomials, but I just wanted you to be aware that there is this other type of asymptote. All right. Now, let's talk about properties of rational functions. So say we have a rational function. One thing that you can do, okay, sometimes we do this to manipulate an equation, is we can take our p of x over g of x, and we can multiply the top and the bottom, we just have to be consistent, with another polynomial. And remember, polynomials include just constants. Our next one, here, we have two different rational functions. They both have the same denominator. Because they have the same denominator, we can combine them into one term. And it doesn't matter if we're doing addition or subtraction. This rule holds for both of them. For multiplication, again, we have these two separate functions here, and they're being multiplied. Well, with multiplication, we can combine both of these rational functions into one rational function. So our new numerator is p of x h of x, and then our denominator is g of x q of x. Now division, similar to when you divide fractions, how you do this is you leave the top part, our p of x cubed x, because remember, we can always do big divided by and then divide by the second part here. But then the h of x over q of x, what we do is we switch to multiplication and we flip the top and the bottom. Okay, and those are our basic properties for rational functions. Now let's do a few examples. Let's start off with this one here. So notice that on the top, we can factor out 4. And then instead of 8x, we would have 2x. And instead of 16 here, we would have a 4. In our denominator, we just have a 4. So using that first property, these 4's, we can get rid of them. And we're going to be left with 2x plus 4. Now we could leave it like this, but if we wanted to, we could also factor out the 2 to get the following. Now what about this one here? Our variable this time is a y, and now we have quadratic equations on the top and bottom. So to simplify this, it's going to be easiest to factor them. If you have a hard time doing this, you can use the quadratic equation. But when you're factoring, remember that you get this number by the multiplication aspect of FOIL, and you get this number by the addition aspect. So you want to look at the last number, your constant, and see what factors give you 12. So 12 and 1, for example, 6 and 2, 4 and 3, but whatever numbers you pick, if you add or subtract them, they have to give you this middle constant here. Okay, so I know that I'm going to have y plus something and y plus something. How do I know that it's plus? I know that it's plus because I have a plus here and a plus here. Now, if I pick 4 and 3 and add those, I'm going to end up getting 7. So I have a 4 here, and then I have a 3 here. Now for the bottom, this time I have a negative here and a positive here. Because I have a negative here, it means that one of these terms will have a plus and one will have a negative. Because if you multiply a positive and a negative value, you are going to get a negative value. But whatever those terms are, when I add or subtract them, they're going to have to give me a 2. So if I picked plus 3 and then minus 1, I would end up getting that 2. All is good. And now, this is all multiplication, so I can cancel the y plus 3 on the top and the bottom. For this next problem, we have two rational functions being multiplied together. So the first one, the numerator, we can factor out a 3, which means that we will have x plus 3. And then we can leave the 6. For the next one, I'm going to leave the 18, but on the bottom we can factor out a 5. And remember, these things are being multiplied by each other. And because of that reason, we can get rid of the x over 3. Now, the first function, what do we have left over? 3 over 6, which is the same as 1/2. And then we have 18 over 5. So if we get rid of this factor of 2 on the bottom, I'm left here with 9. And we have 9 over 5. This next one, we're going to factor the top and the bottom. So I'm going to need an m because I have pluses in both the cross term and the linear term. I'll have plus and plus. 2 times 3 is equal to 6, and when added, it gives you 5. So this is a 3, this is a 2. I have an m plus 3 here. And now for my second function, I have an m on the top divided by, I have an m plus, and 2, I get from 2 times 1. If I add those, I get a 3. And now, since these terms are all being multiplied, I can cancel out the m over 2 on the top and bottom, the m over 3 on the top and bottom, and I get m over m plus 1. This next one, careful, we're dividing. our rational functions. So for the first rational function here, I'm going to factor out a 9. So I have p minus 4 left over. This is going to be divided by 12. And now I flip the second function. 18 is now on the top. And I have 5 times p minus 4. Because now everything's being multiplied, I can get rid of the p minus 4. I can get rid of one of the factors of 3 here. So I have 3 over 4. And then I have 18 over 5. We can further simplify this, and we can get 27 over 10, because we can get rid of one of the factors of 2 here. All right. This next function, we have to make sure that there's a common denominator. Instead of multiplying this whole rational function by the denominator of the second term, and the whole second term by the denominator of the first term, you can do it, but it's a little bit messy. It'll be easier to first factor the bottom. Maybe we can simplify the terms, or maybe the multiplication process to get a common denominator just won't be as difficult. Okay, so 3 times 2 will give us 6, and added will give us 5. And then we have 5x divided by 4 times 3 will give us 12, and when added it gives us 7. So we can factor this out as x plus 3 and x plus 4. And now notice on the denominator for both the terms, we have an x plus 3, x plus 2, and then x plus 4. So if I multiply this whole thing by x plus 4 and this whole thing by x plus 2, then the bottom terms will each have x plus 3, x plus 2, and x plus 4. Excuse me. Oops, sorry. X plus 4, x plus 4, and then I'm going to have x plus 2, x plus 2. And now we can take both the terms, put them together, and on the numerator I have x plus 1 times x plus 4 minus 5x, and that's being multiplied by x plus 2. I'm not going to expand the bottom, x plus 2 times x plus 3 times x plus 4, because I mean overall I want to simplify these expressions, but we do have to expand the top and then simplify it. So I'm going to get x squared plus 4x plus 1x, which is 5x, plus 1 times 4, which is 4. For the second term, I'm going to go minus and go big brackets to make sure I don't mess up my negative signs, or hopefully don't mess up my negative signs. 5x squared plus 10x. And now all of this is divided by x plus 1 times x plus 3 times x plus 4. For convenience, I'm going to bring this over to the next page so I can more easily see it. Okay, so here now we have an x squared minus a 5x squared, so this is going to turn into minus 4. Now this term is gone. And then I have a 5x minus a 10x. So that is going to be plus minus 10. This is just going to be minus. And then that's gone. And then the second expression there didn't have any constants. So I end up with this. And we would finish this off by using the quadratic equation or factoring. We're going to finish off this part in class. All right. Now let's try to solve some of these rational expressions. I have to make a common denominator, but one thing I can do first is bring all of my r's on one side, and then all of the constants on another side. So we are going to have r over 10, and I'm going to bring the 3r over 20 onto the other side, but I have to put a minus. And then I'm going to have 2 over 5 2 over 15 minus 1 over 5. So now what I have to do is make a common denominator. So this term, if I multiply and divide by 2, I'll get 20. And here I have a 15, so I have to multiply the top and the bottom here by 3. So I'm going to get 2r minus 3r over 20. And then I'm going to get 2 over 15 minus 3 over 15. We're going to erase these so they're not in my way. And this is going to give us minus r over 20 is equal to minus 1 over 15. The minuses are going to go away, and we're going to cross multiply, which means I'm going to multiply this up to here and this up to here. Okay, so we're going to get, minuses go away, so we're going to get 20 over 15. And I can write 15 and 20 as 4 times 5 and then 5 times 3. So I'm left with 4 over 3. For this one, I'm going to try to simplify it a little bit first. So I have my 2 over x. I will have to end up multiplying the top and the bottom by the x plus 2. X plus 2. And then I have my minus 3x over x plus 2. And this I'll have to multiply and divide by x. But on the right-hand side, notice that I can factor out an x here. And then I have an x plus 2. Now, I can get rid of my x's here. And because for every single term, I have an x plus 2, you can basically get rid of a factor of x plus 2 in every denominator, because it's like multiplying through by x plus 2. So what do I have left over? I have 2 times x plus 2 over x minus 3x squared over x. And then on this side, I just have 1. I'm going to bring these together and expand the top. So 2x plus 4 minus 3x squared all over x is equal to 1. So I'm going to cross multiply again. I'm going to bring this x all the way up here. So I have an x. And now I'm going to bring everything to one side to write it as a quadratic equation. So I have a 3x squared plus 2x. I'm bringing that 2 to the other side, so I have an x. And then I have a plus 4, and I have that this is equal to 0. I can get rid of the negative out front of the x squared if I want to. I don't have to. But I usually prefer just having it positive there. Oh, like we have here. And then I can put this into the quadratic equation. I can go 1 over 2 times 3. And then this is all be multiplied by minus b, which is minus 1, plus minus the square root, minus 1 squared, minus 4. My a is 3, and my c is negative 4. So I will have a positive value. I have 1 over 6. This becomes a plus. And then I have plus minus. So we have 1 plus 16 times 3, which is 48. Okay, or we can write this as 49. And the square root of 49, this is 7. So my first solution is going to be 1 plus 7, which is 8 over 6. And then 1 minus 7, which is negative 6 over negative 6. So I'm going to get negative 1 and 4 over 3. All right, everyone. Well, thank you so much for your attention. I hope you have a great day.